Today we discuss our metric topology. Topic in study of topology. So we will study today the definition of metric topology, some examples, some related topics with metric topology. So let's start. Before we start this topic, I appeal to all of you. If you have not subscribed this channel, subscribe this channel to get other videos which were uploaded by me, and in future if I upload, you will get the notification of my videos. So subscribe this channel. If you like these videos, then like and share with your friends. And any further suggestion if you have, then comment. Let's start. First, I say what is a metric. I lodge a video on this topic. What is a metric? I am again explaining what is a metric. Metric is defined a function from a cross. Uh, take a set, non-empty set, a non-empty set A. Now D is a function which is also called distance function from the cross product of the set X to this is X to X plus X to set of real numbers. So this is a function which have to satisfy some following properties. The first property is that this function with any two elements in X, like xy, must be this distance must be between the two elements in set X must be greater than equal to 0 for each element, for all elements xy in X, and it will be and yeah and d xy will equal to 0. The equality holds. Here the equality sign are given. This equality holds if and only if x is equal to y. Otherwise, it always be greater than 0. Second example is symmetric. That the function is symmetric with respect to any two elements of the set X. This is equal to dyx. For each of the elements, for each pair of elements in the set X, this symmetric property must hold. And third is triangular inequality. This is any three element if you will consider, then the distance between two elements and the distance between uh, any other two elements, taking one from it, this is yj, taking, so it must be greater than equal to dx. This is for triangular inequality for any three element, triple element in X. For all x, y, z, this must has to be fulfilled. J belongs to X. If these three assumptions is satisfied by any function, then it is called a metric of the set X. It is called a metric called a matrix on X, and the space with taking the set X and the function D. These are distance function called it's called metric space. So these are the preliminary knowledge of the metric space. Now, how a metric space generates a topology in any set X. This is our topic, metric space. So we have to consider first that what is the definition of open balls. We now first introduce the definition of open balls. Then we generate topology from metric space. Open balls. So open balls are called if we consider any element. I am drawing a picture here. This is a diagram. There is a single element, any element X. This is the center at the center of the circle X, and its radius is considered epsilon, which is very small positive quantity, not equal to 0 but greater than 0. So such kind of ball is called open balls. So it is written in this way: B X epsilon. Uh, these are called open balls. So here if you will take any element in this ball, open balls. They are called open balls centered at A. So now if you take any element Y, this is any element Y, then you can take the d xy, distance of xy. This is a metric distance or distance function must be less than epsilon. So based on the metric, the open balls are defined. That any any distance between any two elements must be less than epsilon. Then uh, then at any point you can generate a open ball. Here also generate an open ball. Here also you can generate an open ball. So the 2 points carries 2 open balls. Now if you will take the collection of all the open balls for a set, then we can generate a topology for the set X. Let's take a collection. Let's consider a collection. We consider a collection of open balls. Collection of open balls. Collection of open balls. The amount is infinite number of open balls. Means how much you can generate. This goes to infinity. Means infinite number of open balls. So this collection carries. So this collection I denote with beta. Beta is the collection of all open balls. This is all open ball where X belongs to the set X. X belongs to the set X. So for being beta a basis for a topology, we have to fulfill 2 axioms. If you previously seen my videos, I have given a video that where I have told 2 axioms for a basis have to fulfill to generate a topology. So first axiom is that I am writing here. First axiom is that all the elements in X, the finite number or infinite number of elements in X must be covered by the open balls in the collection beta. So you can look this. If We'll take all the collections beta of open ball for every x. For all x, then every element y for any element in x must have a open ball in the collection beta. It must there must be a open ball b y epsilon in the collection beta, the collection which belongs to the collection beta. So this is the first exam is fulfilled, and second exam is that if you will take any two open balls b1 and b1 and b2 and intersect them b1 b2 both belongs to the basis uh, of the collections of the open balls. Then if we draw a picture like in the here, I am taking a open ball here b1, this is b1, and I am again taking and it's this is open ball b1 at the point x I am taking, which have a uh, radius delta 1 which is less than epsilon, and again I am taking another open ball at the point y, this is the open ball b2, and here I am taking the radius delta 2 which is again less than epsilon. So now here the intersection point b1 intersection b2, we can also generate the open wall. Here we can also generate a open wall which is uh, if there is any point z and its radius is minimum of its radius I am taking del which is minimum of less than minimum of del 1 and del 2. So here it is clearly understood. So here its radius, the ball's radius will be del which is less than minimum of del 1 and del 2. So you can generate very easily for any two open balls intersection a new open ball whose radius is less than the other two balls radius. So you can get the open ball B for these two open balls intersection uh, for each of the point Z, and Z is any point. Z is any point for all the points Z belonging to X. So you can look this that the two axioms is satisfied and beta is forming a topology basis for a topology for the set X. So this topology is called matrix topology. This is the definition of matrix topology. Matrix topology. We will study some examples. So matrix topology generation, you have understood how through matrix we can define open balls, and through open balls the collection of open balls generate a basis for a topology for the city A. Now take an example. Let a standard matrix. We are taking a standard matrix D for any two elements x, y, and we consider first a set A. We consider a set A, non-empty of course, non-empty, non-void, non-void set X. Here the matrix is defined in this way: mod of the difference between the elements x minus y. So this matrix we will now prove that generates a matrix topology for the set X. How? Here it is for all x, y in the set X. So now how it can be proved? We have to define open balls, open balls, open balls B X epsilon. So these are the open balls by defined by this metric by this metric function. Here all the any element y belonging to this ball open ball b x epsilon, it will be dxy. So any the distance between any two elements dxy is equal to equal to mod of x minus y. Difference must be less than epsilon. So such kind of balls we will take where the difference of two elements is less than epsilon. This is our open balls defined in this way. Now, such kind of open balls can generate a basis for the topology for the topology on the set X. So we will take the collection again beta of all the open balls B x epsilon x epsilon. So now we have to verify two axioms that all these open balls defined in this way uh, contains or covers all the elements in the set X or not. First example can be satisfied in this way by describing that if we will consider uh, so if you look this definition here, each of the element satisfies each of the elements satisfied or the this definition that each of the element must be carried out by a open loop. Each of the elements satisfies this definition and each of the element must belong to a open loop. So first axiom can be checked out very easily by this open balls definition. Must belong to a open B I am taking. And the second one also we can be checked out in this way that if we will take the intersection of two elements, like again I am drawing a diagram. This is B1, this is B2, this is B1 and this is B2. Now if this is X, this is X and I am taking this is Y, there is Y, this is Y. So X minus Y is less than epsilon and the diameter is equal to epsilon. So this is I am taking again delta 1. The same logics will work here as I have described. and again here it will take the element z, and here I am taking z1. You can do this. Here I am taking the radius del 2. So in this intersection we can generate any open ball which also have consist 2 points. Here in this open ball we can find out 2 points, like take AB, which satisfies this, like AB, A minus B mod of A minus B must be less than minimum of del 1 and del 2. Minimum of del 1 and del 2. The diameters, the radius of the two open balls. So you can generate a open ball at centered A, like a open ball centered at A and its diameter less than minimum of del 1 and del 2. So minimum of del 1 and del 2. So this open ball exists in the intersection of the two open balls B1, exists the intersection of B1 and B2. So here for each element for A, you can find out an element in the neighborhood of A, which is a open ball, and also this open ball is carried out by the two open ball intersection. So in this way we can fulfill the second exam. So this topology, this standard matrix, is generates a topology for the set X. So if we take in place of X R, then it will be a standard matrix. D is called standard matrix, and the topology is called matrix topology on R. Standard topology matrix. So here we will get the matrix topology, which is if we will consider the R, then the matrix topology is actually we will find out the order topology. The matrix topology is coincide with the order topology on R. This matrix topology coincide with the order topology of the real set of real numbers R. Now, if X is a topological space, if we consider a topological space X, a topological space logical space X, and if any matrix, there exists any matrix D, which induces which induces a basis for the topology, or a metric topology on the set X, the metric D. If there exists any metric D which induces a topology, metric topology on X, then which induces a topology. So here topology can be generated by a basis, directly cannot be obtained. So there must be a basis by the matrix defined by the matrix. So this matrix defines a basis which generates a topology for X. then we will call that X is metrizable. Then X is set is metrizable. So this is the definition of metrizable. That we must have for any topological space X, we must have a matrix which also generates the topology for the set X. Then X is said to be metrizable. Metrizable. So there are many topics related with this, and just I finish with defining the metrizable, the definition of metrizable of any set, and keep on to watch my video. I very soon discuss more topics on metric topology. So, thanks for watching.